My name is Majid. I'm joined faculty, as Randy said, in July. A lot of my research interest has been around substance use. Um, Sorry, I want to make sure there. I don't really have anything to disclose except that the work I'm going to be showing you today is going to be kind of the culmination of some of the K work that I'm finishing up in my fifth year, and then our new R01 that got awarded in September. And I think I'll start by saying I'm not an addiction specialist, so I welcome criticisms. And secondly is a lot of times people refer to me as the dude married to Elizabeth Salisbury Afshar. I know Elizabeth's been faculty with your group, and so you guys may recognize the similar last name, and she does all the important work. So I'm just here to share some of the research that she helps to criticize and fight against. And so she's actually across from me now, so she's keeping a close eye on me. Okay, a little background. So 25% of my effort is spent in the ICU, and that's really my experience with substance uses and folks that come in intoxicated or in withdrawal that require management in our intensive care unit. But the majority of my time is spent running a data science lab, and this is kind of the life cycle of what we tend to do in our lab. We have a pretty large group, and I co-lead it with another physician scientist, but essentially we like to focus on kind of the end-to-end life cycle of data science. We like to develop models and really build them inside our lab that are intended for improving health outcomes using electronic health records. Our focus has been in hospitalized folks, and so we do a lot of work around internal, external validation, and nowadays with bias assessment and decision-making analyses. And then we do want to go, a lot of our work and some of the things that we do for our grant funding is actually build the user interface and do the testing with human-computer interactions, and then put these into a trial setting, such as a quasi-experimental study or cluster randomized or whatever that may be, and really trying to implement these things into practice. So, we have the expertise in our lab to kind of do this end-to-end type of work. Now, I'm going to start kind of where my K began, in that I apologize, the slide's a little bit fuzzy, but in the trauma center I was at previously at Loyola University, it was a level 1 trauma center. They were initially doing audits on folks as part of the expert kind of requirements to remain credentialed with American College of Surgeons as a level 1 trauma center. And, the fidelity around that is, despite their best efforts, they're only getting about 60% catchment for screening. And so then they transitioned to using blood alcohol concentration and using the blood alcohol levels as kind of a screening tool. And anyone that came in with a positive test, they tested. And so some of the work that had been emerging more in literature around forensic sciences and some of the outpatient setting care, or some of these other direct alcohol biomarkers. And so this diagram here kind of illustrates some of the things that you guys may be familiar with in terms of indirect markers that previously been used, like liver enzymes and GGT and CDT. And towards the bottom are some of the more, kind of emerging biomarkers that are direct metabolites of alcohol. So alpha-glucuronide, alpha sulfate, those are metabolized by the kidneys, and less than 1% of what is consumed in alcohol, and can be markers that can actually detect up to several days out. My focus has been in phosphatidylethanol. This is a biomarker that actually is formed in the presence of ethanol in whole blood. And this actually and it's only formed in the presence of ethanol, and this actually can stick around for, half-life of up to several weeks out, especially in heavy daily users. And it's got a lot of different species. It's got about 40 different homologs, and we kind of examined one of the more common ones that's kind of in humans. And so that's kind of the work that we had focused on, trying to see if this biomarker would be useful for screening more comprehensively. And so the study that we did was actually a prospective study, multi-center, where we enrolled we screened everyone that came in through our trauma center. So this consort diagram, you can see that over a course of 2 years, there were about 1,600 adult trauma encounters that came in through a level 1 center. And our research associates kind of did the screening, and obviously there were a lot of exclusions for different reasons, a lot of them being that, it was past the time frame on weekends or evenings. But we enrolled the kind of our sample size requirement to kind of meet the study requirements of 250 plus patients. And Randy, this might be something we may want to do for our second aim in R1, where we kind of capture the same type of information across all hospitalized patients and what the RAs are able to screen. And then using the audits, using cutoffs of 5 and 8 for females and males on the 10-question audit questionnaire, We use that as our baseline reference standard to identify those with any level of unhealthy alcohol use and those with no evidence of unhealthy alcohol use. And so we actually did the studies internally with internal validation at Loyola University, and then we partnered with UCSF and did our external validation work over at their level 1 trauma center. And you can see that there are differences in the cohort characteristics between our sites, which actually is very helpful for external validation. And so, the UCSF group had a younger group, less folks with white race, more non-Hispanic whites in the Loyola group. Rates of unhealthy alcohol use were kind of what we expected in trauma centers, around a third or so, and that seemed to be consistent with what we saw across these two sites. Injury severity score, the ones that they were able to enroll in and consent had more severe injuries at UCSF, more positive blood alcohol levels in their group, and then a little bit sicker group in that they had longer lengths of stay and fewer got discharged home. So nice although they're both level 1 trauma centers, some differences in characteristics. Sorry, this is also a little bit blurry, but essentially what we did for this study is, we kind of hypothesized what is the best biomarker or combination of biomarkers to screen for unhealthy alcohol use. And so we examined across the more popular biomarkers that are currently in practice. So, blood alcohol concentration, CDT and GGT, which are the indirect markers, and then urinary ETS and ETG, ethyl glucuronide and ethyl sulfate, as well as PEth. And you can see here in the first set of columns, the univariable median values. Obviously, the PEth values had a pretty large range between anywhere from 90 to 600, which is kind of typical for what we may see in the more heavy alcohol users, blood alcohol concentration, and some of the other urinary biomarkers. And the odds ratio for actually identifying or predicting those with unhealthy levels of alcohol use, PEth was by far had the highest odds for be able to identify that. And in this study, what we did was we actually did a multivariable approach where we did kind of a machine learning algorithm where we actually did a least absolute square selective operator to identify what is the best combination or choices of biomarkers. And in this scenario, we kind of looked at a variable importance measure that kind of weighted how these variables played against each other. And across both these metrics in the multivariable model and the variable importance measure, again, PEth kind of showed us to be the most important. Now, the reason urinary ETG and TS kind of zeroed out is because it was highly collinear with PEth. And so it was actually shown that it wasn't actually contributing much more to what we knew from getting PEth levels. And so once we gathered these cohorts, we kind of ran the area under the curve for discrimination and got receiver operating characteristics, and then we identified the best cut point on that curve to kind of serve as a screening tool for any level of alcohol misuse. And the optimal cut point that we identified to kind of meet a certain sensitivity threshold that we wanted to get at without losing too much specificity was 25 nanograms per milliliter. So at that cut point of 25, an internal validation of the first set of numbers, we had sensitivity and specificity of 95 and 80%. And then in external validation at UCSF, we still kind of stayed above 70%. Now, obviously, it was a smaller cohort. It was a convenience sample, so we weren't powered for that one, but we still, which is why the confidence interval is a little wide, but we still show pretty good metrics. What was interesting is that you probably could reclassify that and actually do better, because we had a lot of false positive cases that we went back and looked at where these patients self-reported no levels of unhealthy alcohol use, but they came in with positive blood alcohols. And in fact, almost a quarter of them had levels above, what's considered legal intoxication at 80 milligrams per deciliter. So, I think this is not uncommon that we do see the underreporting on these audits. And then when we tried to see if there was a combination, as people are trying to identify what is the best screening tool, we actually didn't find that combining variables together was any better than phosphatidylethanol alone as a biomarker. And so this is a decision curve analysis. Essentially what we did here is on the x-axis, we looked at the net benefit in a decision analytic measure that puts the benefits and harms on the same scale and is useful for clinical decisions. So here the net benefits, it's a formula that takes into account sensitivity, prevalence, specificity, and the predicted probability or the probability for having alcohol misuse on an odds scale. And then I'm sorry, that's the y-axis. And then the x-axis is the actual predicted probabilities. And what you see here is that the gray line is if you were to screen everyone, the black line if you weren't to screen, and if you were to screen no one. And then blood alcohol was actually the screening tool that was being used currently at both UCSF and Loyola, and then we compared it to PEth. And you can see that, and this decision curve kind of weighs relative harms of false positives and false negative screening. So the diagram shows the scenarios and for across these biomarkers and screening everyone and no one. And you can see that PEth, for the most part, is kind of above that curve, regardless of the decision threshold that the provider may have in terms of they want to capture more patients but accept more false positive, or capture less patients and accept have more false negatives. And across the spectrum here, aside from a few dips there, and kind of for the most part, PEth did better than blood alcohol. And so this is a common tool that's used, and when we kind of validate these metrics before we put them into practice to see if there's actually potential utility in replacing what's current practice. Now, the issue that we have with these biomarkers is that they're performed on these liquid chromatography mass spec machines, which is not common in labs. And I think this is the case here at Wisconsin too, is that if you guys want to check PEth, it's a send out, right? So we don't have a point of care method. And so this kind of made me rethink, while this is a promising measure that we can potentially use in the future and hopefully will become more readily available, it's not really something that I can take with and run interventions around or do kind of practice behaviors for. And so this kind of comes back to this question of what is our learning health system cycle, and trying to be able to analyze and assemble data that are being used in practice and kind of see how that changes our practice behaviors and kind of reiterate this process. And so that's kind of brought me into the field of electronic health records, and our lab is focused on data science activities. And so really our focus has been taking some of these statistical methods, and as machine learning has evolved, we kind of evolved with these methods to kind of take leverage of these masses of data available to us. And in the context of substance use, 80% of our notes are of our EHRs in the note format. So it's a huge mass of data that's difficult to mine, right? Substance use is frequently, at least mentioned in the admission, right, notes in the H&P, capturing a social history. It's not that far off from the single question of for alcohol use, or single question for drug use. And so you can imagine there's probably a lot of information those first 24 hours of notes that can get at some of these behavioral conditions. And patients are more likely to disclose to their primary care provider or the primary care team than a screener that may come in as kind of more of a stranger to the patient's care and with a directed question around drug use, which may be what contributes some to the underreporting in terms of stigma bias and recall bias also contributing. And moving forward, when I'm going to use the term opioid misuse, and essentially that's any non-medical use of opioids or illicit drug use like heroin and such. And so can we leverage the data in electronic health records? So these are counts from my previous institution where, you guys may be familiar with these note types, right? Progress notes, H&P notes, op notes, consult notes. And these are snippets that kind of come out of these things where, it's not uncommon where there may be some quantification of the alcohol use to have, or in the HPI, there's mentions of it. So, how do you really tease these out and be able to take this qualitative information and quantify it? And so this is kind of some of the expertise that we hold in the lab, which is called natural language processing. And essentially this is taking these clinical documents and be able to mine and analyze them in an annotated format. And some of the methods that we use in our lab come from kind of what is developed out of IBM, which is this UEMA, this unstructured management architecture, where these documents are fed in, and there are these tools, annotators, modules within the software that teases out elements of the document that are then serve as a metadata file called an XML file, which is data about data that we can then use for analytics. And I'll go into this a little bit more, but in the clinical realm, we use something called the Clinical Text and Knowledge Extraction System, which is a software tool. And so what does this tool do? So this is an example this is a mock note, but essentially it can go through these notes and tag mentions, right? So it can tag what are signs and symptoms, what are diseases, what are medications. And by tagging this, it's doing what's called name entity recognition. So we're actually getting these concepts mapped out of these notes, and we're actually able to identify these entities and use them and feed them into modeling procedures. The National Library of Medicine has invested a lot into these approaches, and so The NLM runs the Unified Medical Language System, which you guys may be familiar with. It's the meta thesaurus, so anything from SNOMED IDs to LOINC codes to RX norms, even the ICD and HCPT codes and all that stuff. So I kind of congregate into this kind of meta thesaurus. And so what happens is that these are all codified, standardized medical vocabulary. So now what CTIX, that NLP software I told you about, the engine can do is it can take that raw text note, scan through it with its annotators and all the things, and with high accuracy, it can actually map out mentions in the notes to these concept IDs. And so what you're seeing here is a screenshot of my account on UMLS where I can go and look up something like opioid abuse. And you can see there's a bunch of codes, these C codes called concept unique identifiers, which are linked to these mentions of different ways opioid abuse can be identified, as well as kind of different how it's capitalized, what syntax it's in, even synonyms to these things. It can actually map all those to the same vocabulary. And so heroin overdose.
It's just a fancy word search, right? It's a word search by a supercomputer.
Yeah, I guess you could say it's a little bit more than kind of a rule-based keyword search, but essentially it's a method in natural language processing called name entity recognition. And so there are some machine learning that, because you have to account for, Mike, you have to be able to know negation, like when it's saying it's not heroin overdose, and how is the semantics and lexical ambiguities between sites, the way someone describes heroin and maybe how it's described in the West Coast versus East Coast, and the language that's used in the notes can vary. And so there is a little bit more sophistication, like you said, in terms of how these actually mapped so we're getting the same concept ID. So what we do in the lab is essentially then we feed these notes, right? So we kind of do our analysis at the encounter level. So for every encounter that comes in, so a patient that has 60 encounters, over the course of 3 years, we'll take that individual encounter. We'll take all the notes that have occurred in that and concatenate them or combine them into one single text stream, run it through our CTIX machine, get the codified concepts out of it. Now we have like this kind of structured version of the notes that we can feed into machine learning algorithms. And so this scenario is a supervised task where, like, for instance, you have the audit, which tells you what's the reference standard of what is unhealthy versus healthy alcohol use. And what the algorithm will do, will figure out, okay, what are the combination of CUIs or these concepts that are helpful to identifying those from the notes versus those without. And so we do these as inputs into the model, and then we have the target, whether that's the audit or target CUIs or whatever reference label. And this is the term that's considered supervised learning. And so one of the first things that we did was we did this in a linear fashion, in that we did this for unhealthy alcohol use. So back at my previous institution, we took these CUIs, these concepts. We also took the raw text features. We kind of processed them in the way I described. We fed them into a supervised learning task. So in this case, it was a logistic regression. Unlike the logistic regression you guys may be familiar with, we use regulation parameters that kind of zeroed out things that were highly correlated and changed the weights around, and did this across multiple iterations until it figured out what was the best performance on an area under the curve metric. And the reference data set, the gold standard we used here, was the audit. So it trained on this, right? We did use 80% of the data to train, and we tuned the parameters of the logistic regression model. And then we did a holdout test data set where we actually tested it, and those were the metrics that we actually reported. And so we did this across about 100,000 notes, and there were 11,000 unique concepts. And we still compare this to kind of what you guys may want to do as a rule-based keyword approach, saying, hey, what if we just looked at kind of the keywords of alcohol dependence, alcohol abuse, alcohol withdrawal, alcoholic. We compared it that way. Can machine learning do better than that? And like ICD codes, when you do these keyword approaches and claims data approaches, they have very poor sensitivity, right? You miss a lot of people where they don't do explicit mentions of these things, but there are a lot of things in those notes that are associated with them. And so we actually had a much better performance when we did this machine learning model. Here you see an area of the curve that got up to near 0.8. And then on the left there is a calibration plot, which is actually looking how well the observed and predicted match, whether they're cases or not cases, across different predictive probabilities. And so if we were to run this algorithm, we would have identified another, a quarter of the cohort was essentially missed because, the audits couldn't have been done, or they were underreporting. And just to give you an idea, out of this logistic regression model, where again, we ran this thing called LASSO, which is least absolute shrinkage and selection operator, these are the positive concepts that came out that were the stronger predictors. I don't have the beta coefficients here, but essentially the terms like ethanol, lorazepam, victim, these have face validity to you. There are some things in here that don't quite make sense, but you have to understand it's looking at 11,000 concepts, and it's looking at multiple combinations of how these concepts can work together. And then some of the negative things like having hypertension or things like coming in for pain or other things were actually found to be some of the negative predictors. Now, again, a lot of these terms make sense, but there's going to be in a list of 11,000 terms. I'm only showing you some of the top ones, and certainly this is a little bit simplified form of how the model kind of identifies cases and non-cases. So we took the model and we actually took it out of the trauma unit and we ran it on the hospital cohort. And we found that when we ran on the hospital cohort as kind of another internal validation mechanism, the sensitivity and specificity, PPV and MPV, remained pretty good. We were pretty happy with this, and the area under the curve was high. And in fact, when we look at this on the curve there, when we actually went back into chart reviews, we did this across 1,000 patients. We found that we could, tease out the frequency or quantity of drinking as the model was getting higher and higher in its predicted probabilities for having unhealthy alcohol use. The frequency and quantity of drinking went up and up as well in our chart reviews. And so that kind of provided some additional validation. Okay, so I've introduced to you guys sort of some of the more conventional methods in natural language processing and some of the linear modeling approaches to take those engineered features of the notes and feeding them into a classifier. I'm going to go to the next step in kind of the evolution of this field in data science and talk about deep learning now. And so when I talk about deep learning, it's for the most part, it's about neural networks. And so I think the way, for those who aren't familiar with this, you can think about it is think of just hundreds of logistic regressions happening at the same time across each other, looking at multiple different interactions, multiple different models, and updating the weights as we do this to find the best combination of features. And this could be done across layers, and that's where you go from shallow to deeper layers. Now, some of the tasks don't require that much sophistication. And in this case, it didn't need to go that deep, but this diagram essentially shows you how we take all the CUIs, right, the concepts that we talked about, and in this case, we had 10,000 of them, right? And instead of building a 10,000 column-wide table, we actually compress this so that the machines can handle this computational load into 300 dimensions. And rather than treating as 0, 1s, we actually treated that 300 dimensions as an integer across 0 and 1. So like, the mention of heroin abuse would be 0.1, 0.35, 0.6, 0.7, essentially a vector that represents, it's basically a number that represents heroin use. And the reason that's important for later is because now you can actually get to vectors that are similar values because they're similar meaning. So heroin use and, prescription opioid use could be more related to each other than heroin use and asthma, right? And so those vectors will actually be similar in value. And that's what's called an embedding. And so that's an important concept in NLP because now people are doing a lot with embeddings to actually get these kind of vectors that are representations of words, but they're also vectors that can be similar in values to represent semantics and meanings of the words across these vectors. And so these can be fed into these deep learning models. And so we did this for opioid misuse. So in this situation, we did the same thing. We took the CUIs, the concepts. We also took the words themselves, character-based. Here you can see, if you follow this diagram, the words heroin, cocaine, all these different mentions and notes are transformed into the CUIs, right? And then they're fed into these embeddings. And that's what I was describing, is that now this CUI is represented as this vector. And this is what's called a convolutional neural network. And it's kind of what people use for image analysis to kind of look and scan across pixels. And what it does is that it learns baseline representations of opioid misuse in the first layers, and then kind of gets more complex in understanding the combination of these characteristics to get at a phenotype. And so what happens is it goes through this kind of neural network, and at the end it spits out a probability, and then we do a yes, no for opioid misuse. And this is still supervised learning. So in this situation, we did 1,000 chart reviews to identify cases with experts. This is where Elizabeth kind of weighed in on how to train our trainees in a lab to identify opioid misuse. And so we trained the data and we kind of tuned all the different parameters of the model to get the best area in the curve. And then we tested it on a holdout data set. And when we did that, the point of this table is just show you the complexity of all the different experiments we can do in terms of the different types of neural networks. I'm not going to go into detail here unless people have questions, but we kind of compared our different approaches of these nonlinear models, these neural networks, to our linear models, to our rule-based models. So Elizabeth and a psychiatrist helped us come up with sort of like using between drug screen data, ICD codes, and some other things. Can we come up with a structured rule-based approach and compare these across the board to see if the increased complexity really matters? And we found that our CUI-fed neural network actually did pretty well. It actually outperformed for the most part across a lot of the metrics. And so you can see here we got PPV and positive predictive value, negative predictive value above 80%. And so we've actually published this and shared the code, the source code, because it's CUIs, because these are concepts, it's de-identified data. As you know, sharing notes is not easy to do, but when we convert it to this format, it allows us to do it. And so we put this up as a software tool that is open to the public under an open source license so that other health systems, other investigators can go and download it and test it out and run it in their cohort. Now, this could be used for screening. It could be used for cohort identification. It could be used, a lot of different applications. So we partner with our collaborators at Rush University because they have something called the Substance Use Intervention Team and Program, where in 2017 they've started manually screening all their inpatient hospitalizations for substance use. So they've attempted, they kind of built up a system where they did a single questionnaire screen and that led into an audit or DAST. The 10-question audit or 10-question DAST. And so in this situation, we used the data that they had used for manual screening to test and silent test against our algorithm. And so, they ran the DAST on everyone, and those that screened positive on a DAST, they asked what is the type of substance use. And so you can see here, this is kind of a diagram of, they got about 56,000 of their 80,000 inpatients screened between 2017 2019, and then towards the bottom, we kind of use anyone that had either just opioid use alone or any opioid use plus other drugs as identified by the DAS to be the kind of the labeled cases, and then everyone else is kind of the unlabeled cases. And so when we ran our algorithm against this cohort, when we identified again the optimal cut point, we were once again getting, a positive predictive value above 70%, negative predictive value really close. I mean, because the prevalence was so low in this group, it was actually it would certainly affect the positive predictive value more because it's easier to predict negative cases than positive cases. So your rates of false positives will go up. And so when we ran this on the first 24-hour notes, because we essentially wanted to run this tool in real time, knowing that patients could get hospitalized and can stay for a few days, we were able to get also similar metrics of negative predictive value was really high, specificity that was really high, and the sensitivity that was 75%. And essentially what happens is when we kind of calculated what this would look like, so for every 2 alerts per day would flag positive for every 100 patients, and that kind of matched the prevalence that they were seeing in their hospital. And so the number needed to evaluate, which if those who are familiar with the number needed to treat, this is kind of the corollary to that for screening tests, and it's just a 1 over the PPV. In this case, it was 1.6 people needed to evaluate to accurately identify yes or no for a positive or negative case. So right now, I've talked to you guys a lot about some of the predictive analytics in terms of these metrics of sensitivity, specificity, area in the curve for discriminating, but obviously there's more to it than that. And so when we want to deploy these tools in practice, we really have to consider, especially with stigma around substance use, what is fair and equitable across different subgroups in terms of, different races and ethnicities. As you change prevalence and settings, the model may actually not look the same. You may have to update it. And then these black box models really need some explanation to gain the trust of end users like ourselves, right? And so this is some of the work that is part of R01 and looking at that. This is a calibration plot, which I've shown a little bit earlier in some other slides. And so on the left here, you can see that, the perfect calibration where what's predicted by the algorithm matches what's observed in the proportion of that cohort. So that would be essentially a slope of 1, kind of that straight diagonal line through this. And then anything that kind of falls below that, you're over predicting. Anything that falls above that, you're under predicting. And then you can see certain subgroups can fall off. And so that's kind of an example on the left. And on your right is actually what we experienced when we went from Loyola to Rush, because when we trained the data and validated at Loyola, we were doing on a kind of a sampling approach on medical records, and the prevalence was closer to 20 to 25%. And then we moved to kind of all hospitalized patients at Rush, prevalence dropped to 3%. So you can imagine it's not surprising then that the algorithm would overpredict. And that's what this line here shows you, is that this line being kind of flat and doing that, it's overpredicting across all probabilities. And so we actually had to recalibrate it to account for this. And so we were able to come back to a better fit line, which is expected and recommended in terms of these running these tools. Is you have to update these models as policies and practice changes, as well as recalibrate them as you change in prevalence across settings. Then the next thing we want to look at is, okay, you know, is this model fair across different subgroups, right? And so this, without going too much detail, this is looking across different subgroups of non-Hispanic Black, non-Hispanic White, different sex groups and different age groups. And so I'll kind of draw your attention to, and we looked across multiple metrics. These are things like false discovery rate, false negative rate, negative predictive value. But if you look at the false negative rate on the bottom left here, and anything in red is kind of is unequal, in that we took the methods out of employment practices where people looked at equity, saying that if you're more than 20% outside your largest reference group, in this case be non-Hispanic whites, and your metrics are 20% outside of the variance of that, there's some inequity that's occurring there. And so that's what the red represents. And so you can see that non-Hispanic whites, the non-Hispanic Black group, there was a lot higher false negative rate, right? And so people were being labeled as negative when they should have been labeled as positive. So we were essentially missing more non-Hispanic Blacks. And so we didn't want this to obviously occur at scale. So there are a couple options here, and we couldn't go back and retrain the data and identify these bias. So what we did instead is we actually went back and calibrated the data so that it would actually better fit for non-Hispanic Black group. And when we did that, you can see that the false negative rate then came back in line to green with the non-Hispanic White group, so that we weren't actually, perpetuating inequities across our screening rates. Now, it's a zero-sum game. So while we improved the false negative rate, the false detection rate increased a little bit in the non-Hispanic Black group. And so this brings up another ethical issue. Is, okay, now we may be perpetuating stigma here, because now we're labeling more non-Hispanic Blacks as positive cases of substance use, when in fact they're not. And so this is work that we're still working on, researching, because we know there are better methods than what we're offering here in how we do this. This diagram is a little complicated, because I do want to highlight that these are important things that are going to become more pervasive in our practice as time goes on. And I think this is something that we value in our lab, that we train medical trainees and people with clinical backgrounds to come through and understand, because predictive analytics is going to continue to kind of drive innovation in a lot of ways for clinical decision making. And so what this graph shows you is, obviously what we're comfortable with are the linear models, right? The kind of logistic regressions and some of the tree-based models and stuff like that, where we can actually understand all the variables in the model, how they interact with each other and what they represent. And that's kind of in this kind of green shaded area. Then there are the kind of the nonlinear models, where there are approaches within them specifically that allow you to kind of tease out what's causing the decision and the predictors that are making the decision for whatever task you're doing. For instance, adversarial neural networks, right? What that is they kind of introduce kind of falsehoods into the model to see if the model can tease out what we know is false versus what's right, to show if there's if it's understanding the task correctly. Separately is something that we've started working on, is these post hoc methods in this kind of yellow area. And so what happens with these machine learning models, because they're such complex black box models, sometimes you have to do a model on the model to kind of help figure out what is that model trying to learn, or what is that model trying to tell you is the most important thing. And so one of these methods that we do is something called local interpretable model agnostic explanations. And that's kind of a fancy term for basically taking our black box model, like the neural net model I showed you earlier, and kind of taking a single case out of it and running a linear model on it, like a logistic regression, to try and figure out, of all the predictors it's kind of worked with, what are the ones that's finding to be the most strongest features. And so we did this for our convolutional neural network, which was for the opioid misuse thing that we validated at Rush. And we went back to the trained model from Loyola, and we actually looked across what the model was thinking was the strongest predictors for labeling opioid misuse, and looked at it across these groups that had some inequity in the way they labeled positive and negative cases. And what was interesting is that, this is just a snapshot. It's a very surface level view. This is just looking at the top 20 or 19 features across, hundreds and thousands of features. But what you can see is the most important features here in the non-Hispanic white, again, kind of makes sense, right? We're seeing a lot of mentions of cocaine, drug abuse, heroin's in there, methadone, polysubstance use, and then some of the maybe other medical complications that come with these hospitalized patients. And similarly with the non-Hispanic Black group, I think we're seeing similar terms, but I think the only difference is kind of the order of these things, in that it's showing that heroin is a much stronger predictor in non-Hispanic Black group than non-Hispanic white. And I think if you look at the epidemiology in Chicago and Chicago area, that is kind of the more characteristic of opioid use among non-Hispanic Blacks. Okay. So, this is kind of that prior to deployment, what are the most important things to kind of look at to make sure that when we scale this up, we're not causing harm and we're actually serving a useful purpose for screening. This slide is actually something that's ongoing currently at University of Wisconsin. Randy's kind of helped inform some of this, but essentially we have in UW Health Operations under John Long, under Cheryl Goswami, who's the Chief Information Officer, and John Long is the VP. They have an advanced analytics group, and they're currently building a real-time machine learning NLP pipeline, and they're using our opioid misuse as a use case. And it's a lot easier than it's a lot more complicated than I state, because it's taken them about 200 man hours to actually build this pipeline, just a technical piece of it, because it's very difficult to take notes as we're writing them in Epic or in HealthLink, feed them out into another space, which is what this shows here. It goes into Cloverleaf. And what we're doing from Cloverleaf is once the notes are extracted out into this interoperable platform, we're actually feeding it up into the cloud, into Microsoft Azure. And in Azure is where we do our analytics. So here is where they downloaded my software to run the classifier in Python to actually make the predictions. Makes the predictions off that note, and then comes back out of the cloud into an Epic cloud system that can feed it back into HealthLink. So then it would be coming up to you as a BPA or as a flag or whatever format we want the end user to receive that. So I think I just kind of want to share this because this is something exciting. There's not many health systems in the country that are really doing this in real time. And I think we're kind of moving in that direction at UW. Now for health outcomes research, right? We want to put this into a clinical trial setting. And right now we're planning to do this at Rush. And at Rush, they currently have a manual screen in place. So we can't do this as a randomized clinical trial because we can't, there's already something there that's happening. And so what we're doing instead is an interrupt time series design, where at the start of the intervention, we're going to turn off the manual screen and turn on the automated classifier screen. And then we're going to kind of see the differences pre and post, and kind of get a sense of does this actually lead to more consults, and does it lead to improved adherence with their expert program. And then a secondary outcome is looking at readmissions and adverse events afterwards. Now, I've been talking separately about substance use as alcohol misuse, separately as opioid misuse. I think sometimes you're looking at the tree in the forest in these situations. And so at least in Chicago and what I'm at least observing in Wisconsin is that it's really sometimes a polysubstance use issue, right? And so we wanted to look at this using kind of a unsupervised or a kind of a latent approach to kind of using statistical measures to see what are clusters or groupings that we're seeing. And so at Loyola, we took the entirety of our EHR and we ran something called latent class analysis, which essentially just is a clustering approach or a class identification approach without us using it, telling it what to do. We give it some class defining variables and it clusters out groups of individuals. And we found that a 4-class membership was actually what came out to be the best model fit, which is the figure here. but we found different groups with different proportions of polysubstance use that had opioid misuse. There was a heavy alcohol use group that was in older patients. There was a group that had a lot of illicit opioid type use with low SES. We actually linked our data to the public health data to get poverty index data. And that group also had a lot of mental health conditions. There was this group of kind of one and done in our health system that came in through the trauma center. Younger cohort, a lot of positive urine drug screen data, and then this non-alcohol related hospitalizations and these people who are more chronic users, higher income, older age group, kind of prescription drug use. And we actually found that across these classes, they had differing outcomes. The group that was heavy alcohol use and the mental health conditions had higher mortality. A lot of those with mental health conditions left AMA. The class 1 group, which was the group with non-opiate related conditions, had high readmission rates. And so these actually led to meaningful outcomes in terms of what we noticed differences in. We also wanted to kind of see, okay, well, what are the notes matching what the structured data we're doing? Because so far we've only looked at kind of the ICD codes and urine drug screens and comorbidities. And so we did something called topic modeling, where actually we went through all the notes and we used, again, another kind of latent class analysis approach, in this case called latent Dirichlet allocation, to kind of figure out what are important themes that are coming up in the notes of these folks with opioid misuse. Without looking at the clustering that had already been done, we wanted to kind of get a general sense of the topics that are showing up. And so what we found was that there was a lot of topics around respiratory diseases, alcohol use in itself, polysubstance use, mental health conditions, things that we were seeing in the claims data that were actually showing up in the notes as well. And here you can see we actually looked across all those concepts and we built out these topics. And we came up with 20 topics as kind of the best number of topics that had the best fit, and looked across those classes of people like, the high alcohol use group. In the notes, they came in with a lot of intoxication and withdrawal symptoms, right? And they had a lot of pancreatitis. They had a lot of GI-related conditions with their alcohol use. In the low SES group and illicit drug use, they had a lot of mental health conditions that were noted and documented in the notes. And then the trauma group, they came in for burns, traumas, and recreational drug use. And so it was a nice face validity approach for us to kind of take the entirety of the EHR, where we use the notes to kind of match what we were seeing in the structured data to get at these important topics. So what? So this is kind of what led to our one, is that, we didn't want to just look at single substance use. We didn't want, we built this classifier for alcohol use, we built a classifier for opioid use, but it's a polysubstance use problem, right? And so we actually want to build a new classifier that can identify all types of substance use. And in this case, because of sample size requirements, what I'm showing here is basically what's called a multilabel classifier, which can in one algorithm identify if someone has any one of these combinations, not exclusively, but can be overlapping. So someone can come and have all three, one of the three. In this case, we're looking at non-opioid substance use, opioid use, and alcohol use. We're actually taking this one step further and using technology that's used in a self-driving car like Tesla and other things, where you actually learn from your environment. So we have these labels, and then we actually want to bring in other things that are useful that can help the model maybe understand better the nuances. And so here is called multitask learning, where we actually bring in ICD codes, Lichthauser codes for things that we know that are risk factors in terms of, HIV and mental health conditions and other comorbidities and other questionnaire data, to not be the primary label that we're trying to get at, which is the substance use, but be what's called auxiliary labels that can help at least inform how we learn the primary label. And this is a machine learning approach that has become a lot more prevalent and gaining performance. And so this is kind of the experiments we're running now in our lab. Now, in the last 5-10 minutes, I just want to take you to the next level here, in that this field has only advanced, and it's hard to keep up because it's really the private sector driving this. So companies like Google, Microsoft, OpenAI, Elon Musk's group, they have hundreds of engineers and billions of dollars dedicated towards this, and this is really an advancing field in NLP. And so I'm gonna try and finish here by talking about what we're trying to do next to kind of align with the advancements in the field, which is called language modeling. What is that? So language modeling is actually saying, okay, we don't need to start from scratch anymore to build these classifiers, right? We don't need to say, okay, we're starting from not knowing anything. What if we actually understood language in itself, and that we actually could understand meanings of words and the context of these words, how the word order is shapes up, and what sentences should come after each other. You guys may have seen this in the news and things like that. But essentially, Google kind of did a landmark paper in 2018 where they actually took the entirety of Wikipedia and a bunch of books, and we actually did this thing where they predicted 15% of the words that they masked in those to kind of come up with a way to build a baseline hierarchy of language understanding. And so this is a very advanced form of a neural network that can actually takes everything from the internet that's only grown in the amount of data they use to try and learn kind of word order and meaning and stuff like that. Now you have this baseline understanding of language. Now let's apply it to our task that we want for our classifier. So now we take it into the EHR data, and then we tune it to against the audit or DAST or whatever to try and predict cases or understand if someone's going to have complications or whatever task, what's called fine tuning to get the final model. And so in the clinical domain, this is happening right now, and that people are taking, text sources like PubMed and Wikipedia and training and building a vocabulary out of it and learning how this vocabulary works in terms of understanding the words and stuff like that and applying it to certain tasks. Burt is kind of the Google version of this. It stands for bidirectional encoder representation from transformers, which is just a type of neural network. And they do what I described earlier, which is they mask out 15% of the words in the input and then do this modeling to try and predict those 15% of the words, and then they can fine tune it for whatever task they want. And you guys are using this actually. The Google search engine right now runs on Burt. In the background, it is a language model. And before, when you type in, can you get medicine for someone, pharmacy, it would just give you a Medline for getting a prescription filled. But now it actually understands what someone means in that context. And it can give you a more directed response to what you're actually asking. Now, I'll tell you that this field is, since 2018, when Burt came out, has only grown. Now, Burt had about 300 million parameters in the model. OpenAI in May just came out with one that had 150 billion parameters, okay? Meaning that these neurons or features, it had 150 billion versions of these things to understand language. Google just published in the last several weeks one that's 1 trillion parameters. So is that more neurons than our brains? There's a lot of controversy right now around these language models because they can certainly write news articles and respond to you intelligently, and you wouldn't know you're talking to a machine, but they may be giving you the wrong advice. And so in the clinical domain, there is something called Dr. GPT-3 that one of the AI labs was testing. And, on the left and right here, you can see how it can cause harm, and that it's following a dialogue with you. And the left, you're kind of giving symptoms of a DVT, but it's telling you to go stretch because you have a sore muscle. And the right, it's telling you that, you're depressed and you're saying, should I kill myself? And it tells you it should. These are real life examples now. So this is actually the language model. And GPT-3, which is the most recent one, they haven't published the code for this because they know that this can cause, a lot of harm. And I think we've seen this in social media where there's these bots and things that are coming in and pretending to be people that when they're not, okay? Now, this is not to say that we can't leverage this technology and try and learn from it and use it. And so in this case, we actually took something like this, and we took a version of Burt because Google shared their code with the public. And so we took that code and we engineered it for our task, which is predicting ICD codes. And so what you can see here, what's interesting is that when we did it just off the language model without any additional training data from the EHR, it actually achieved what's called an F1 score of 7.740, which is just a harmonic mean between positive predictive value and sensitivity. And that did almost as well as our kind of focused, fine-tuned, trained model on just opioid data from the electronic health record. We're talking about a general domain model that just learned off Wikipedia without any medical knowledge or focused task, was able to do almost as well of a prediction of identifying opioid misuse cases than our version that we've done in the lab that's focused on EHR data that was hand annotated and identified. I think there's only about 7 minutes left, so I'm gonna probably skip the remainder of these slides, but essentially what we're talking about here is taking a lot of these methods and like like those concepts I described, what if we mask those concepts and we're able to predict concepts? Or what if we predicted all the ICD codes? We can get to our own version of a pre-trained model in the EHR. And this is something where I'm trying to push here at UW, is that we have an off-the-shelf pre-trained model where no one needs to start from scratch anymore. We can actually start with an understanding of some of the, what are the medical, and like be able to predict the common medical conditions or understanding of some of the language and medical text. And we've actually done experiments to show that when we do this approach, it's almost as good as a supervised learning approach. This is called self-supervised versus a supervised. And so we've published work showing that, yeah, there's benefit here. And so coming back to the experiments we're doing for the polysubstance use classifier, I had described earlier a multi-label, multitask. But what if we brought in a pre-trained model and then did the multi-label, multitask? So we're not starting from scratch anymore. We're actually starting from a better understanding of medical language. Now, future work here is, I think in addition to the health system, one of the things that I'm on the chi-square and I'm working with ICTR to build a learning health system module is that we want to build a registry where we bring in pre-hospital data and we bring in fire, police, ambulance, public health data and use these algorithms as well to kind of uncover emerging patterns of substance use, prognosticate who are people that are going to come back and have encounters with police and fire. You can imagine that there could be a lot of potential applications of this. And this is a second R01 that's going to be under review in about a week. And so we're hoping to do something in this in the public health informatics context, but this is just a kind of a snippet of the future. So I'm going to stop there. I want to thank you guys for having me. We're a collaborative group. We have a lot of partners across the region. I've been fortunate to have funding from NIDA and IEEE. We are part of the clinical trial network. I know Dave Gustafson's on this call, but essentially NIDA has a clinical trial network. We are, Wisconsin's a site in the Great Lakes node, so there are funding opportunities there for people that want to do intervention trials or clinical trials. We're kind of the data science piece to that group because they want to do more informatics work. Our lab is a handful. We have about 3 postdocs, 3 master's level data scientists, and I co-lead the lab with Matt Tripek, who's another physician scientist. So I'll stop there, and I thank you guys for your time.